I'm just going to give like a quick talk about one of the techniques that we're using. It's in the works to accelerate sparse MLA via something that we're calling masked MHA. The key word in MLA is really latent here. So if you see on the left, that's kind of like a classic multi-head attention projection. So you have your hidden states, and then you have weight matrices to project that. So you have WQ, WK, WV. MLA is what you have on the right. So you have a WQ tensor to get your Q tensor. But then instead of having separate K and V tensors, you just have a single WKV that projects into like a low dimensional CKV. So you just have one KV representation. And if you look in the bottom left there, you can see our hidden dim on like a classic MHA. The equivalent would be about 16,384. We're compressing that into just a dimension of 512. There are actually two different and equivalent ways to compute MLA. And the first is what we call MHA style. So in MHA style, you take that compressed CKV tensor that you made earlier, and then you multiply it by some up projection tensors. So you have WUK and WUV, that's a typo there. And then you get your normal K and V tensors, and then you compute attention MHA style like you normally would. And when you do this, each QK product is over the true head dimension of 128. The other way to compute MLA is what we call MQA style. So instead of up projecting your CKV, you're going to compress your Q into the latent space as well. And now you have your Q prime and your CKV, and you compute attention directly over CKV in this latent space. And so what you're paying by doing this is larger map moles, right? So you're actually each attention operation is doing 3.4 times the flops, but you are actually getting way less memory traffic because you're dealing with the compressed tensors rather than the full representation. And this pairs really nicely with the kind of like prefill decode split that we deal with a lot in LLM serving, because in prefill, you are compute bound, right? So you want the most compute friendly possible implementation. And so we use MHA style for that. You get the smaller map moles, you have some more memory traffic, but because you're compute bound, you don't really care. Whereas in decodes, your compute bound, your data movement bounds, memory bandwidth bound. And so you don't really care that you're spending a little bit more flops because you have vastly less memory traffic. DeepSeek 3.2 kind of built on MLA by introducing sparse attention. And to give you just a general sense of what that is, you can see at the top, let's say we're generating this sequence here. vLLM is a fast and easy to use library for LLM inference and serving. And so let's say you're generating that last token, the query token is serving. Perhaps you don't care about attending to all of the words in your context. Like the stuff that might not be as important. And so you can save on the cost of this long context by only attending to the tokens that are most important. You can see kind of in the bottom left, a visualization, that's your CKV tensor from before. Really, all you have to do is pick out a few rows from that tensor to attend over. And if you visualize your attention mask on the bottom right, you can see that row at the very bottom. That's what you're doing for this decode, right? So you have your query token all the way at the right, and then there's just a few highlighted cells, tokens that you're actually attending to. Now, with prefills, the situation is a little bit different, right? Because now you're computing this entire thing, not just the bottom row. And so now you can't just pick out, for example, a handful of these tokens to gather into your shared memory on your GPU, because at some point you're going to touch all of these tokens, right? And as implemented in vLLM right now, we only have the MQA pipeline implemented. And so the optimization that we're doing now is to implement MHA, that MHA pipeline, but instead we're going to pass a mask, this top K mask into our MHA kernel that tells it which tokens to attend to. And we do this in kind of like a efficient bit packed way. And that allows us to take advantage of the compute savings of the MHA pathway. And so the result that we get is up to about a 2x speedup for the attention operation in this sort of moderate seq length band. So on the top plot, you can see the blue line corresponding to MHA and the orange line corresponding to MQA. You can see that as you get to longer and longer sequence lengths, you eventually hit a threshold around 7740 where MQA starts to be better. But below that, there's a region where MHA is faster, and it can be up to 2 times faster. Now, there's actually a second threshold down at the very bottom, very short sequence lengths, 136 tokens, but we can actually ignore that with a second optimization, which is that if I go back to this last slide here, if our sequence length is short enough, our top K is such that we're just attending to every token in the sequence. And so when we're in that kind of regime, we can just run normal dense MHA. And so for DeepSeek v3.2, that top K is about 2048. And so we don't even need to worry about that. So now we kind of break up our MHA or our MLA pipeline into 3 regimes. We do dense MHA for very short sequences, masked MHA in the intermediate regime, and then sparse MQA at long contexts. And that's going to give us nice speedups across the board.